Hello, I'm Tate from the University of California, San Diego, and I'll be showing you how Alan, Sorin, and I tamed wildcards in Java's type system. So first, what are wildcards and why do we use them? Well, here's an old Java program for averaging a list of numbers. Note that this program uses a runtime typecast. These things are undesirable for a variety of reasons, and so we want to get rid of them. One way to do this is to add generics to the language, so that I can say nums has to be a list of specifically number. And the problem with this is that now I can't use a list of integer or a list of double, all of which would have worked in the old program. To get around this problem, you can use bounded polymorphism to say, I'll take a list of any p that extends number. This polymorphism is a little awkward though, because this type variable is being used only once. And so with wildcards, you can actually say, I'll take a list of some type, I don't care what, so long as that type extends number. And the program will still type check. Note that because this list type is actually not covariant, you can't use declaration side variance to deal with this problem. You actually need this use side variance annotation here. Wildcards are more than just a convenience though. They actually make the type system more expressive. Consider this program here, although don't look at all its details. This is something you might write when doing reflection in Java. And what's important to notice is that this type here is actually inexpressible with just polymorphism, in particular because it's impredicative. Also, this method down here is actually untypable with just use side variance. You need a concept known as capture conversion in order to type check this method. The way you want to think of the type class super p is really as there exists an x such that x is a supertype of p and this is a class x. This existential interpretation of wildcards is essential to understanding how Java's type system works and why it's so expressive. Unfortunately, with all this expressiveness comes a number of challenges. Because of these challenges, there's a number of open problems with wildcards. For example, there's actually no known subtyping algorithm for wildcards, even though they've been around for 7 years now. The subtyping rules in Java are actually overly restrictive, meaning there's a number of types you'd expect to be subtypes which aren't according to Java's language specification, and the Java compiler, javac, actually has a number of special handlings in it to accommodate for these cases. The join algorithm for wildcards is incomplete. I actually ran across this problem in a class of mine where my students were confused to why the program wasn't type checking, and when I took a look at it, I determined it was because of this join algorithm incompleteness problem. These problems have been well known. However, there's some new problems that we've identified. We determined that the Java type checker is actually non-deterministic because of some complications with intersection types. We also determined that the type checker can even affect the semantics of your program. This is because type inference can infer different types, and how these types interact with method overloading can actually change the semantics of their program. Now, the contribution of our work is that we've solved these problems, except the last one, which could still use some significant improvement. Unfortunately, I don't have time to go over all these solutions, so I'm just going to focus on this first problem and talk about subtyping. So subtyping wildcards is challenging for a variety of reasons, and I'll illustrate a few of them now. The standard subtyping algorithm used currently is broken in a variety of ways, and I'll show you 2 examples of this. First, here's a class numbers, which is a specialization of ArrayList for handling numbers. One might wonder, okay, is list numbers question mark a subtype of list question mark extends number? And not knowing the answer, what you might do is type up a little program and ask the Java compiler, okay, are these subtypes? And if you did, it'll tell you no, these are not subtypes. And this is worrisome because if you actually look at the Java language specification, it says yes, these should be subtypes of each other. So your Java compiler is lying to you, not intentionally of course, but it's rejecting programs that you'd expect to be accepted. Another interesting program is this class here, which I won't really give any tuition for because it's rather bizarre, but now we're going to consider, okay, is C of x a subtype of D question mark super Cx? And again, type up a little program to ask the Java compiler, and what it'll say in this case is Stack Overflow. It won't even give you an answer, it just crashes. So clearly, this answer is wrong. So now look at the Java language specification, and it says no, these are not subtypes of each other. And what's interesting here is that we actually determined that this answer is also wrong. It's actually more consistent for the Java language specification to accept these subtypes for reasons we explained in the paper. So now, to give an impression of what's going on here and why there's these challenges, I'm first going to focus on this program here. I'm going to put the subtype at the bottom and the supertype at the top. So the Java language specification specifies subtyping in terms of direct supertypes. So a direct supertype of list numbers question mark is list question mark extends numbers question mark. And a direct supertype of that is list question mark extends array list question mark. And a direct supertype of that is list question mark extends list question mark. And these are not subtypes of each other. And so you might mistakenly think that list numbers question mark is not a subtype of list question mark extends list question mark extends number. The problem is that every type has many direct supertypes. And so really you're searching a graph here. However, this graph is infinite, and so you can't really afford to explore the whole graph. Where we went wrong in this case is that because of this constraint on the type parameter numbers, we actually know that this question mark here is implicitly constrained to be a subtype of number itself. And so another direct supertype of numbers question mark is array list question mark extends number, and a supertype of that is list question mark extends number, and so we show that list numbers question mark is actually a subtype of list question mark extends list question mark extends number. To avoid this problem of searching paths, we actually throw away the concept of direct supertypes altogether and even transitivity, and instead we consider the two types side by side. Because both sides are in terms of lists, what we do is we instantiate this wildcard as numbers question mark, and then using recursion we check whether this constraint holds after instantiation. So next we check whether numbers question mark is a subtype of list question mark extends number. Here what we do is, since we have a wildcard on the left side, we open that wildcard as a fresh variable x, and we add any constraints on that wildcard to the context. In this case, there are no explicit constraints on the wildcard. However, because of this constraint on the parameter, x is implicitly constrained to be a subtype of number. Now what we do is we use inheritance to phrase both types in terms of list again, taking advantage of the fact that numbers x is a subtype of array list x, which extends list x. This allows us to instantiate this wildcard, and then again, we use recursion to check whether the constraint holds after instantiation. Now, we simply assume the constraint from the context, showing that these two types are subtypes of each other. What we've shown is this algorithm is sound and complete provided it terminates, meaning that if it tells you yes, the types are actually subtypes of each other, and if it tells you no, the types are in fact not subtypes of each other. However, it may not give you an answer because it may never terminate, which brings us to the next major challenge of wildcards, which is non-termination. So now, consider the other example I showed you earlier, the one that makes a Java compiler crash. What we're going to do is apply our algorithm to illustrate what goes on here. First, we apply inheritance to get both sides in terms of D. This allows us to instantiate the wildcard and then recursively check the constraint on that wildcard. This time, since we're checking a super constraint, the two sides sort of swap places. Now we use inheritance again, and then we use instantiation again, and then we recurse to check the constraint after instantiation. What's important to notice is that at this point, we're effectively at the same place that we started at. We've just replaced x with L of x. And in fact, you can use this process to construct an infinite proof that these two types are subtypes of each other. These infinite proofs are problematic because they mean that an algorithm can always be making significant progress towards its goal, and always be going in the right direction, and yet never reach its goal because the goal is infinitely far away. To solve this problem, what we did is we noticed that this program here is completely contrived. People don't write programs like this, and so one way we can solve it is by simply disallowing these contrived programs. This solution is not as easy as it sounds because, for one, you have to make sure to restrict the language enough that you can guarantee termination. Yet, you can't restrict the language so much that you disallow programs that people do actually write in practice. Smith and Cartwright conjectured that if you disallowed something known as expansive inheritance, you can guarantee termination. However, we show in the paper that this does not work. And so we had to come up with a new set of restrictions after carefully analyzing the algorithm and how it works. In particular, we identified two classes of programs which, in unfortunate circumstances, can lead to non-termination for our algorithm. To prevent this first class, what we did is we restricted the inheritance so that you can't use question mark super when specifying the class hierarchy. For the second class, what we did is we restricted the way you can constrain parameters, allowing you to use question mark super only at covariant locations and constraints. What we proved is that with these two restrictions, our algorithm is guaranteed to terminate, meaning it will always give you an answer, and furthermore, that answer will always be correct. Now, as you can see, these two programs are contrived here, and so you might wonder whether this holds always. To check this, we did a survey of 9.2 million lines of open source Java code, including things like Eclipse, NetBeans, and even the Open Java Development Kit. In the inheritance, we found is that there is not a single use of question mark super in all this code when specifying superclasses. And for constraining type parameters, there were 2% of cases that used question mark super, and we examined these 2% and found that all of them were at covariant locations. In fact, all of them were at top level locations, indicating that we could restrict the language more in order to give a more useful or user-friendly error message. So in summary, out of 9.2 million lines of code, there was not a single violation of our restrictions, suggesting they're in fact very practical. So I've just shown you a subtyping algorithm for Java which is both sound and complete given very practical language restrictions. However, this is only a small part of our paper. We also provide a theory of existential types, in fact, infinite existential types with infinite subtyping proofs, which incorporates the concept of implicit constraints that I mentioned earlier in the talk. We also provide techniques for type argument inference, such as a way to lazily join wildcard types in order to deal with the incompleteness problem I mentioned earlier. We also provide fixes to the type system, such as an improvement of Java's concept of type equivalence, as well as improving Java's intersection types to deal with the non-determinism in type checking I mentioned earlier. We provide a number of extensions to Java which would be compatible with our algorithms should Java choose to take them, including some discussion on how to mix use site variants and declaration site variants safely with wildcards. Thank you for your attention, and I hope you've enjoyed this talk. Please contact us if you have any questions or comments.